development system, etc., and kind of push you into their world, have you buying Pixie chassis, so you're not even buying a normal computer, you're buying like a computer with a backplane, kind of like VXI stuff and all that kind of stuff in the back in the day. So we wanted to make something that's a bit more open. Use what you want, use Python, use C, use our stuff, plug it into our stuff, make it work, plug it into a CAN network, plug it into our competitors' equipment, make it work, it's not a problem. So we wanted to make it very open and economical, I will not lie. If you look at some of the devices, especially devices that are analog to CAN, those devices usually start out at about $2,500 without isolation, and then with isolation you're up to $5,000. And so when you start to do the channel count and say, this is how much money I have to spend per channel, it can be astronomical. Now those other devices are really good, they're very durable generally, but in many applications you don't need to have IP67. Okay, usually you're mounting things in the trunk or inside the passenger compartment. Sometimes you're in the lab and you just don't need to have something that's super rugged. You just need something that works well. It's always nice if it's inexpensive. So I'm going to give you an introduction to the RAD-IO2 series, and then I'll go into some more specific module information, a little bit about how it connects and the software that you can use. And then if I have some time, which I usually don't, but I do have some specifics about isolation and some other key things that are important. A little bit about sample applications too. So essentially, we have a whole product line of these slices or modules, if you will, that can actually fit together and be daisy chained together. And so you can actually do a wide variety of things. The first one that we are coming out with, which we're almost there ready to release, is this RAD-IO2 TC, which this is actually 8 channels of thermocouple. We do have a power relay, so if you want to actually switch some high current relays, we have a module for that. We have an analog out, an analog in, and a digital I/O. So basically inputs and outputs in the same box. And then finally a CAN hub, which is basically to provide an interface that can output CAN or CAN FD. Okay, and also this can power a stack as well. So the idea is to make it open. You may not even need Intrepid. You may not even need a CAN tool. Maybe you just want to do analog data. That's it. Real easy. So you can just simply plug it into a PC. And then we offer a JavaScript program. We offer a JavaScript program so that you can calibrate, view data, and log data to your PC. Or we have APIs for Python or for C. So you can basically do what you want, integrate it with whatever tool you want, okay? Another way would be to connect it directly to the Neovi Ion or the Neovi Fire 2, or that little guy in the middle there is actually, that's actually the Neovi Plasma, which we still make it, but it's very, very uncommon device. And essentially, each of these devices has its own USB port, USB host port. You simply plug it in, it gets power from the Neovi, so whatever power you're providing to the Neovi, it in turn powers the RAD-IO2 system. And then it just automatically records the data and puts it into your Neovi right along with all the other data. The third way is a CAN hub. So basically, the CAN hub has an external power supply, and then it in turn powers the stack, but the output is in CAN or CAN FD. So any CAN device can be used. So that's about as open as we can make it. You know, use it on your PC any way you want, use it in any CAN or CAN FD network, or just plug it right into your data logger. Okay. So to be a little bit more specific, the RAD-IO2 TC is the thermocouple module. We have it in the back actually right now, and you can play around with it. We've done a lot of testing on this to make sure that that it really is a really good performer despite the relatively low cost. So the idea is, and before I go into this, you'll see in the slides several mentions of banks and then channels per bank. It turns out that essentially we're referring to the architecture, but in many cases I'll tell you exactly how many channels it really has, because that's what we really talk about in analog is how many channels do you have. In this one, it is 8 channels essentially. 8 banks, 1 channel per bank. In this case, it's just 8 channels. Okay. So essentially, each of the boxes has 8 channels, and each of those channels does have its own cold junction compensation, and it has its own ADD chip. There is no multiplexing or anything like that. There's no clock skew between different channels. It's essentially simultaneous sample and hold. The one thing that you might think is a drawback, but it's not really that bad, it only works with K-type thermocouples. So the most common thermocouple to use in industry or in general is a J-type thermocouple. So you can have a J-type thermocouple for many applications and many stuff it works, but we only use a K-type, which still gets us well into the automotive range. So basically, even with this very large swing, the -270 to 1260, we still end up with a plus or minus 2% accuracy.
So
or
1260, 1260 degrees Celsius?
Yes, I'd have to look it up just to make sure that's not a typo.
Maybe 260 degrees.
With the thermocouples, yeah, it depends on the type, depends on the junction, but I can look it up and make sure. Okay. Unfortunately, I did not write the slides. I'm not the project manager, product manager for this. Yeah, he's not out here today, so I get to give his presentation. But yeah, I'll have to double check. But basically, the type is what dictates the range, because that's essentially what it tells you the behavior. So it does have 105 dB common mode rejection, and it is isolated. So it is really, in this case, in essence, it is channel to channel isolated. Okay, and believe it or not, this guy is $800. So this would be about, let's see. In comparison, I've seen modules like this that are isolated. They're $5,000. So you're looking at what, 1/5, like roughly 1/5 the cost. Okay, but those modules that are $5,000 are very rugged, IP67. So these are actually still pretty rugged. They're not bad. They have an aluminum case, but they're not watertight. So at this point, we've looked around, and even the companies owned by National Instruments don't really have anything on the market that provides this channel-to-channel isolation anywhere near this price at all. Okay. Now you can potentially do some isolation that uses miniature relays. But when you do that, now you've got problems because you're disconnecting, connecting things, you get settling time, you get errors. Okay. So essentially, what we normally see when we calibrate, we specify that we have a resolution of 0.2 degrees C and that the accuracy of the hardware is plus or minus 2 degrees C. We generally see an accuracy better than plus or minus 1 degree C when we calibrate and test. Okay, but technically what we're releasing to the public, we're telling people it's 2 degrees C. You can test it for yourself and do calibrations through the free software. The analog input, this is where I'm going to have to talk about banks and channels a couple times, because essentially you end up with a 8 different banks, but each of those banks actually has multiple options, if you will. Okay. So in the end, though, it really is just 8 channels. That's the important thing to remember. So essentially, each one of those channels has a low range and a high range that you can connect to. Okay. So either you can connect to the low range to get one of these 3 scalings. So basically, a plus or minus 250 millivolt, or one plus or minus 1, or plus or minus 5. Or if you need the higher ranges, you get a plus or minus 8, 16, or 42 volt. Okay. So there's a low connection, a high connection. You cannot use both at once. Essentially, you, again, only have 8 channels in this box. And the crosstalk in this thing is really good. You don't have, we've done a lot of testing on that to make sure you're not getting influence from one channel into another. So again, the channel-to-channel isolation is very, very good. One thing I don't mention in the TC, but I start to mention here at analog in, but this is true of all the modules. The maximum sampling rate is 2,000 samples per second aggregate. So if I have one box, 5 boxes tied together, you end up with an aggregate sampling rate of 2,000 samples per second. There is also a limitation per channel. I can't just turn on one channel and then get 2,000 samples per second. My maximum sampling rate is 100 samples per second per channel. So I have to observe both of those situations. For thermocouples, not a big deal. Usually you're looking at 1 second or maybe once every 5 seconds. Oh, my bad. But that is just one thing to keep in mind. So if I have 24 channels, I'm going to get about 83 samples per second. Okay. So the bottom line here is actually this little line here at the bottom. It is really the bottom line. This is good for low frequency measurements, voltage measurements for like your VBAT, things like that, where you don't have a lot of transients. But when you have lots of fast transients, if you're using a microphone, accelerometer, a strain gauge, this is not really for you. Okay. So this is good for a lot of measurements you might have in the lab, on the bench, in a car that are not doing a lot of changing. Okay. And that's a very important thing to know. I wish that we actually are already working on the next generation of this. It's going to be a while, but that next generation will be much, much faster. So we'll have a much faster sampling rate. But that's, like I said, it's going to be a while for that one. The resolution on virtually all the products, it is a 16-bit resolution. Okay. So that's always the key thing. Of course, most everything that you deal with nowadays, if it's super, super cheap, it's not even 16-bit, maybe a 12-bit, okay? 16-bit is definitely where you want to be. The analog out is for output of analog channels, right? So essentially I can have analog output. It's not like a relay where I'm handling lots of current, which we'll get to in a second, but essentially the RAD-IO2 out has 8 banks, and each one has 3 0 to 5 analog outputs. So you actually have a total of 20, my bad, hit it too click happy. Why are you doing that, strange? Here we go. 24 channels. So I can actually supply an output of 24, because each of these banks are isolated from each other, but each bank of 3 channels is not, because they have a common ground. So that's important to know. Again, it's 16-bit. The maximum amount of current is going to be 5 milliamp output. Okay. This is something that I honestly have had customers, very few, but a number of customers throughout the years saying, I need to take a CAN signal and convert it to analog output. And this is actually the device that can do that. There's not really many in the world that can really do it. Okay.
I have a quick question here.
Yes.
I'm not typical hardware guy, but I say in a real life, we abandon analog TV for a long time already. It's digital TV. Mm-hmm. But why are we still using the analog device here?
Because the bottom line is, we might be in a digital world, but we still have physical phenomena. Those phenomena are analog.
Really?
Of course. Because
why not make it a digital,
Well,
you can make a digital measurement, right?
Yeah.
Right?
It's a very interesting question, because so the thing is, if I have an accelerometer, okay, what comes out of it might be digital, but that's because I have an analog to digital converter inside of it. I might digitize it, okay, to process the information, but ultimately in lab work, I may very well have something where I need to give an analog output. In fact, I was just talking to a person just this morning about they needed to simulate the brake pedal, and the brake pedal is a resistance, and that resistance would therefore have essentially with a VBAT across the resistance, and it's essentially like a potentiometer. I'm just going to press that brake, and it's going to change the resistance. That changes the voltage. They need to simulate that going into their ECU. It has to be analog.
I see.
So the thing is, we always have this bridge between the sensor and the actual physical phenomenon. And so now you are right. Most everything we deal with is digital. But you have to remember, as soon as we get to this boundary of here's the physical phenomenon, and then we have a sensor, a transducer to get it, then often either this transducer is output or has, or we have inputs that we need to use for analog, or we digitize that so that it's removed from the user or removed from the ECU. So it is important. So it may not be applicable to your particular situation, but the person I was just talking to worked in infotainment, and I was telling him about this and saying, well, yeah, I don't think you need to use this because you don't really do analog. All your stuff is all Ethernet and all this. And he's like, well, actually, and it just happened that, yeah, he actually needs it. So it's not for everybody, not for every situation, but it is important, especially when we're dealing with the physical phenomena. Once we get there, this is where we really need that kind of stuff. So that was a very good question, actually. One thing I wanted to point out, which is something I never really expected, is that essentially this equipment does have some additional memory. So it's possible that we can load up output waveforms, and then you could trigger them through software. Okay, this is not available yet, but it's coming. So if you're interested in that, definitely let us know, because if we get interest in it, then we'll actually improve the firmware and allow that to be done. If not, we'll probably just not do that. It just depends on the interest, okay? But that's actually kind of interesting that a product that is only $800, you could actually program kind of like an ARB or arbitrary waveform generator and say, I want you to generate this signal. Boom, do it now. It's very interesting to me. In fact, I just went through the example of analog output. You have to have analog outputs to simulate the vehicle sensors. So we already covered that. Anyways, the digital I/O. Now, the digital I/O actually has digital inputs and outputs. So you have 8 banks. Okay. Now, but for the first 4 banks or channels, if you will, or I'll just say banks for now. The first 4 are inputs. The second 4 are for outputs. So these first 4 banks are isolated inputs. So you can actually put it up to 40 volts. These are 12-bit, not 16. But there's 3 of the inputs. 3 of the inputs times 4 banks. So you actually have 12 different digital inputs, which are kind of cool. And having them, having the ability to put up to 40 volts into them is kind of nice too. Often, if we don't have signal conditioning in there so we can put in a voltage, then we have to use a voltage divider or some kind of means to bring the voltage down to the level of the processor, which is 3.3 or 5 volts, but you don't have to do it in this case, okay? So, the other second 4 banks are digital outputs, and each of those have 2 digital outputs. So you have a total of 8 digital outputs that you can configure, okay? Make sure I'm staying on track here. Oh yeah, I'm not bad. So the outputs can be configured to pass the 5.5 up to 40 volts. Now, this voltage that's being passed up to 6 amps, you have to supply that, okay? So the box itself is not going to source 6 amps in and of itself, but that's something that you can supply externally so that you can tie it to the channel, and then the channel will give you the current that you need, okay? So that's another half of that same module. So digital I/O gets you digital inputs and outputs in the same box. Now, one other thing that's kind of cool is I can actually use these outputs as PWM. So it does not mention it in the name or anything, and it just has this little mention in the slide, but the reality is, if you need to do a PWM output, then I can actually do that with this box. So that means anything that takes an input, I can simulate the PWM output that's coming out of the device, which is kind of cool. Now the power relay is essentially just relays that you can control through the USB, if you will. So you get 8 200, they're rated for 250 volts and 5 amps. Although something tells me we switched these to actually 7 amp relays. Maybe I'm wrong. Well, let's just stick with 5 amps. So each of these relays that are connected up here can actually deal with up to 5 amps, which is kind of cool. Okay. So each of these contacts, which are really hard to see in this slide, but you can see it in person in the very far back. You'll see that there's actually 4 little contacts in here, and these contacts are Phoenix spring contacts. So you actually see there's a normally open, a normally closed, and 2 commons or 2 grounds. So essentially, you can connect up a normally open for contact closure, normally closed, etc. And this is one thing that's actually kind of interesting. So the enclosure is actually a die-cast aluminum. Okay, we never really intended for it to be used this way, but the product manager decided one day he was going to take it home and drive over the RAD-IO2 with his truck. So I thought that was a bad idea, but he wanted to actually check it out. So I think if I press this button again, it will actually, yeah.
Ooh.
That's pretty amazing.
Good.
So I know at the beginning I talked about, well, our stuff isn't quite as rugged as the other guys. It's not bad, especially when you start to think about the price being a quarter to an eighth the price of some other solutions for the same channels. So it's not bad, not bad. Now to connect them together, there is a dovetail, which if I zoom back here, I might be able to show you a little bit closer. There's essentially a dovetail that runs along the very top, and if I were to flip this over, you'll see that there's actually a dovetail cut into the box at the bottom, so that I can slide these across on top of each other, and they lock together. And there's usually although these pictures don't show it, there's a small detent and retainer that's actually in one corner. So basically you slide it together and it locks, and then you can put multiple RAD-IO2s together into one rack. Often if you get a lot of these, people will mount these together, and we can provide metal brackets in order to attach to that if you need something really robust, because usually sliding them together is just for convenience, but if you're going to bounce them around in a car, you're probably going to want some kind of bracketing. Okay. And I already talked about the spring-loaded push-in Phoenix connectors, which you can see in person at the very back. Of course, the thermocouples use a K-type plug, obviously. So all the modules communicate with it's really a USB-C connector, but technically it's actually USB 3. So we provide a USB-C to a USB Type A connector, like your standard rectangular USB, that plugs right into your computer. Okay. And then to daisy chain them together electronically, there is a small USB-C daisy chain cable that is included with each module. So you can connect one module to the other and they're all daisy chained together. Keep in mind though, each one of those guys draws 200 to 300 milliamps. So if you get a stack of 5 together, that's 1.5 amps. That's a fair amount of current you have to keep in mind, okay? So connection, we talked a little bit about this at the very beginning, but I'm going to talk about it in more detail now. Basically, there's several different ways you can connect up these things to your test or your stuff. First thing is you can actually connect several of these slices together and then plug them into your PC. And then you use JavaScript to program them, to actually calibrate them, actually plot the data and view it, and configure them. Okay, you can also use Python or C. Now keep in mind the amount of current you can supply through the PC may be about 500 milliamps. What you will find though is that some laptops, their USB port is better than others, and so some of them can supply more, some of them will actually supply less. And so when you plug these in, we're giving you the power from your PC. If you have a USB 3 port, it's going to supply more. Sometimes those are rated up to 2 amps. Okay, and so the number of slices you can put together here is directly constrained by the USB port that you have there. Generally, the maximum is 5 in any configuration, and there are ways if you want to tie more together. Then we'll get to the CAN hub, which is usually the easiest way to tie large amounts of these together. And that's just a little screenshot of the JavaScript program. We have it running in the back, so if you want to take a look at it, you can always see that. It's pretty straightforward. And then of course you can do calibrations too. So you can actually do your own multi-point calibration. This is the program we use in production. In fact, we wrote it for production, and now we just release it with a product to calibrate our modules. So you can calibrate them all yourself, do multi-point calibrations. And there's a link that you'll have in the slides that you'll get an email about these later today. If you registered on the website, then you gave us an email address, and I will email to that email address the slides we have for today, and you'll get the link in there too. But basically, if you go to our GitHub, one of the many things we have on our GitHub is actually the library to work with RAD-IO2. Okay. The second way is just plugging it straight into an ion or to a Fire 2 or maybe that plasma in the middle. We basically use that same jumper cable, if you will, to plug directly into the host port. It looks just like what you have on your laptop. Now, the Fire 2 and ion, they should be, unless you have some old firmware, the USB host port should be turned on to supply that current. But keep in mind, the current that you supply to the Fire 2 or ion is what you're also going to supply to this. So you have to make sure you're adding in or compensating for the extra 200 to 300 milliamps per slice that you're going to need. So essentially what happens, although this is very detailed as to how it works, essentially what happens is when you plug it in, there's a certain format where we actually automatically pop up magic CAN messages, if you will. They're actually on what we call the NeoVi network, which is a virtual network, looks just like CAN messages, but they show up separate inside the data, so you can filter them out, but at the same time, they are all time synced with the hardware you plug it into. So it's all fully synchronized, just in a new channel that pops up just to provide the data. And then there's a format in which that tells you which module, which bank, etc., is actually providing the data. And here's the third way, basically CAN Hub. So the CAN Hub is essentially a device that interfaces to the RAD-IO2 and provides out CAN or CAN-FD as you program it. You still have to have an external power supply. We can source up to 3 amps through the CAN Hub to power these modules. So the max we're specifying here is actually up to 5 modules. If you wanted to connect up more, you can actually just connect up another CAN Hub and another 5, and then connect those together on the same CAN line, and they'll all work together. And I've already talked about the CAN Hub itself. And I know let's see, I think we're at that time. Yeah, 1:15. Yeah, I will just quickly touch on isolation, why it's important, and then Chris, you'll be up. So isolation, there's a couple different things to talk about. Channel to earth, so in other words, ground isolation, channel to channel isolation, and then we'll talk a bit about bank isolation, because you don't hear that bank term used in other places. Usually people refer to ground isolation, or they refer to channel isolation. Usually when they say isolation, they simply mean channel to channel isolation, but sometimes people take liberties with that particular term, and they'll say it's isolated, but it's only ground isolated. So essentially, your ground isolation is really that's your most basic isolation. But the problem is, this is the maximum voltage you can have between the ground and your channel, okay? But that actually can be a bit deceiving. If you say it's isolated, that is not going to give you the full range that you really need, okay? And a lot of A/D companies will say it's isolated, and all they mean is it's ground isolated, and that's not good enough, okay? Easy way to show you is actually to jump ahead. Well, let me back up here for a second. Yeah, I'll get to the graphic in a second, I guess. So sometimes they'll use multiplexers to isolate, but that causes errors, okay? But all of our stuff is fully isolated, electronically isolated. Now our banks are isolated apart from each other. So you heard me say banks and channels, and it gets a little confusing. Basically, most devices have channel-to-channel isolation. The ones where there's multiple channels in a bank, those are tied together, but each bank is isolated from each other. And that's up to about 2.5 kilovolts. Okay, so basically, you're thinking, you basically are getting your isolation bank to bank, 2.5 or 2.5 volts, but the RAD-IO2 TC and analog input only have one channel per bank, so essentially it's channel to channel. And I'm going to jump out so we can keep on time. Hey Chris, are you ready?
Yep.